I've been getting some questions that make me think that there's some confusion with the stoichiometry. So I just wanted to go back to chapter 3 and go over what's in there. So the very first thing that you started with was, it went through the stoichiometry for a batch system, and then it went through for a flow system, and then it went through the stoichiometry for a gas phase, and that's where you have a change in the number of moles or a variable volume. And let's see. So then it went through flow reactors with variable volumetric flow rates. So if you're finding that you're confused when you go through your equations, because you write down your design, so when you're looking at these reactor problems, you write down your design equation, and then your rate law, and then the stoichiometry to get the concentrations. And so if you're finding that you're confused with what you need to use for the concentrations, I highly recommend reading chapter 3, because it's pretty good. Like, it's pretty detailed about when to use what and what they're for. So but anyway, just starting out, so stoichiometry, and this is for a batch system. So what you have here is just a batch reactor, basically, and it's perfectly mixed. So then at T equals T naught, you have some Na naught, Nb naught, Nc naught, depending on what your reaction is. And then at T equals T, you'll have some Na, Nb, Nc, etc., just depending on what your reaction is. So then let's assume that we have a reaction that looks like this. We have A plus B over B, B. Well, first of all, I'll just write this as A plus B, B to C, C plus D, D. So then we can make a table, and this is one thing I highly recommend as you're doing these problems. If you're getting confused about what equation to use, or how to, just what equation you need to use for your stoichiometry, then I would recommend using a table, just because I would recommend writing a table, because as you do that, it becomes much more clear where all the equations come from and which one you need to use. So starting out, you have species, and you have A, B, C, D for this. And there could also be inerts. So inerts are things that might be in there that aren't involved in the reaction. So then initially you have Na naught, Nb naught, Nc naught, Nd naught, and Ni naught. And then I'm just going to do a totals as well. So total, you have Nt naught. So then as the reaction progresses, there's going to be some kind of change in the number of moles. So for Na naught, and writing these in terms of conversion x, then the change for Na naught would be minus Na naught x. And the reason why this is minus is because this is reacting, so the A is actually disappearing. And then for B, we can write this in terms of A and x using stoichiometry. So we know that for B, we have minus B over A Na naught x. And then we can do the same thing for C and D, only C and D are positive because we're generating C and D. And then you have, and then with stoichiometry again, you have for every A, you have C over D, this is C over A. For every A, you have C over A Na naught x. And then the same thing for D, so you have D over A Na naught x. And then you have something remaining. So what would be remaining is, so for A, and what's remaining is Na moles of A at time t. So that's equal to what you have initially minus what the change was, so Na naught x. So that's where this equation comes from that we keep seeing, the Na naught 1 minus x. And then the same thing for B, so for NB, this is equal to NB naught minus B over A. So what you have initially minus the change that you had, so B over A Na naught x. And C is equal to what you have initially of C minus the change, so NC naught minus C over A Na naught x. And then the same thing. Oh, and this is plus because we're generating this, we're not losing it. So it's what you have initially plus whatever's generated. So, and then ND is equal to ND naught plus D over A Na naught x. And then for inerts, the inerts don't react, so it would just be N whatever equals N inerts equals N I naught. And so then we can sum all this up. So if we do that, we get NT is equal to NT naught plus D over A plus C over A minus B over A minus 1, because that would be A over A. So then this, if you remember, is delta. And delta represents the increase in number of moles per mole of A reacted. So the change in the total number of moles per mole of A reacted. So the total number can be calculated as, and this is multiplied by Na naught x. So the total number can be calculated as NT is equal to NT naught plus delta Na naught x. So I think that having everything written out like this makes it way less confusing. So then the next question is, well, what if we want this in concentration and not moles? So then to get concentration, first of all, we know that Ca is equal to Na over V. For instance, the first one, if we just divide this by V, then we get Ca equals NA over V, and that is equal to NA naught 1 minus X over V. And then we can do the same thing for B, so we get CB equals NB over V, and that's equal to NB naught minus B over A, NA naught X over V. And we can just keep doing that for all of these. So then one way we can make this a little bit neater is we can define this term that we keep seeing. And I'm going to erase some things real quick. So we can define this term we keep seeing, which is the theta I is equal to Ni naught over Na naught, and that's equal to Ci naught over Ca naught, which is equal to Yi naught over Ya naught. So then we can write, for instance, we can write CB is equal to, so I'll just rewrite this equation real quick. So NB naught minus B over A and A naught X over V. So what we can do is pull out NA naught. So if we do that, we get, right on the next line, NA naught CB is equal to NA naught multiplied by NB naught over NA naught minus B over A X, and this is over, the whole thing is over V. So then we have this, so then we can just say that this is theta B. And we can write the same thing for C. So for instance, we'd have C of C is equal to NA naught theta C plus C over A X over V. So then you can just go through and write this for all of these. So this is a stoichiometry for a batch system. So next I'm going to talk about the stoichiometry for a flow system. Talking about stoichiometry, and this time I'm doing it for a flow system. So this is virtually identical to the batch, except instead of using moles, we're going to use the molar flow rate. So instead of using, so uses Fj instead of Nj. So then we can have this same reaction, A plus BB goes to CC plus D. And so we're going to have, I'll just draw this real quick. So we have a reactor and we have some Fa naught, Fb naught, and then coming out we have Fa, Fb, Fc, Fd. And this is for this reaction. I mean, if you had C flowing in, then you'd have Fc naught over here too, and whatever. So I'm trying to be as generic as possible. So then we would do the exact same thing. So you have species. So we have A, B, C. And I'm just going to go through C on this because that's all I have written down. So first of all, we have a feed rate. So for A, that would be F, A naught. For B, it's FB naught, but this is equal to theta B F A naught. And the reason why is if you remember the definition of theta B is equal to FB naught over FA naught. So then if I plug this in, the FA naught cancels out and I just get FB naught. And this is, yeah, so, and then FC naught is also theta C F A naught. So then there's some kind of, I'm just going to erase some of this. So then there's a change. So the change of A would be minus FA naught multiplied by the conversion. So this is the amount. So this is the percent that's been converted. And so if you multiply that by FA naught, then you should get however much is converted of FA naught. So then we can do the same thing for these other ones. So we know that the amount of B that's converted is B over A using the stoichiometry, FA naught X. And then remember, these are also negative because they're the reactants, so they're disappearing. And then FC is positive because we're gaining C. C is one of the products, so C over A, FA naught X. So then we can go ahead and write what we can write these equations for what's coming out. So FA, FB, so FA is equal to, and remember it's FA naught 1 minus X, but if you remember this is FA, so this is equal to FA naught, so what you have initially minus the change, so minus FA naught X. And FB is equal to FA naught theta B minus B over AX, and FC is equal to FA naught theta C plus C over AX. And then you remember the definition of theta B and theta C. You should, from the batch reactor example, you should know how we came to this. So then we can put these in terms of concentrations. So we know that CA is equal to FA over V, and that's equal to FA naught 1 minus X from here over V. And I should actually write this up here. So this is concentration. So CA is equal to FA naught 1 minus X over V. CB, we can do the same thing for, so CB is equal to FB over V. So then we get CB is equal to FB naught minus, well, I'm just going to write this, okay, so minus B over A FA naught X. So this is actually taking a step back because I get this theta B when I pull out the FA naught, so I'm going to rewrite this. So this is equal to CA naught, actually, FA naught over V theta b minus b over ax. And then this can be rewritten as Ca naught. And this is of course assuming that there's no volume change at this point. So the stoichiometry I'm doing so far for the batch and the flow, I'm assuming no volume change. So that's why I can just say that this is that.